Welcome. I'm Tina Tsou, the TSC chair of InfiniEdge AI at the LFEdge and a TSC member of OPEA at LF AI and Data. Today, we'll explore how PyTorch enables us to develop and deploy the generative AI models across distributed edge cloud. We'll look at why this matters, the challenges of running large language models on resource-constrained devices, and the innovations in PyTorch Edge and XQTorch that makes it possible. By the end of this talk, you'll know how to architect, optimize, and benchmark generative AI solutions that run efficiently on geo-distributed edge infrastructure. Over the next 25 minutes, we'll cover the generative AI and edge computing landscape, including explosive market growth and adoption of statistics. We'll look at the challenges of deploying large language models at the edge, focusing on compute, memory, and latency constraints. I will introduce PyTorch Edge and XQTorch, our tools for running models on mobile and edge devices. We'll discuss distributed architectures and optimizations techniques like model partitioning, compression, quantization, and federated learning. I will share performance benchmarks and a case study demonstrating order of magnitude improvements. We'll finish with best practices and an outlook on the edge AI ecosystem. InfiniEdge AI is a community that bridges LFEdge, LFAI and data, and the broader open source ecosystems to build the generative AI on distributed edge clouds. Our workshop during Open Source AI Week, it's actually tomorrow, covers edge inference, data pipelines, privacy-enhancing techniques, and AI agents running near users and devices. It's geared towards AI ML engineers, edge and cloud practitioners, open source contributors, and maintainers. And the product leaders exploring real-world edge generative AI. Participants will learn how to run generative AI workloads on geo-distributed edges, design the patterns for privacy, latency, and reliability, and see demos using InfiniEdge AI and SGLang. The agenda here includes context and updates from InfiniEdge AI, deploying SGLang on NVIDIA DGX Spark, scaling AI infrastructure, a deep dive into feature emergence and grokking, a hands-on lab and Q&A. Scan the QR code and learn more and join us. The LF AI and Data Foundation is a global community, nonprofit, building and supporting an open AI and data community. We drive open source innovation across AI, machine learning, deep learning, and data. The foundation unites developers and users and industry leaders to collaborate, share best practice, and support development efforts and create new opportunities. Membership tiers range from associate, free, for academic, and nonprofit organizations, through general to and premium levels that offer governance, participation, and board seats. Our committees focus on business intelligence and AI, data ops, ML ops, and machine learning securities. And we collaborate closely with the LFEdge's InfiniEdge AI and the wider open source community. Deploying large language model at the edge is challenging. It's very challenging. Modern LLMs contain billions of parameters and may require tens of gigabits of memory and far more than most edge devices can handle. Self-attention operations are computationally heavy and run slowly on low-power processors, so naive deployment leads to unacceptable latency. We also face trade-offs. Compressing models reduces size but may degrade accuracy. Using lower precision accelerates inference but increase the numerical error. Distributing the model reduces per device memory but adds communication costs. What should we do? And successful edge deployments balance the trade-offs through careful optimization. Generative AI and edge computing complement each other. Running inference on the device reduces latency and protects user privacy by keeping data local. Offline capability allows the reliable user experiences even with spotty connectivity. Adoption is accelerating. 77% of US business are adopting generative AI. 94% of daily users report productivity gains, and 67% feel less burnout. Meanwhile, edge adoption is driven by 5G networks, industry IoT, real-time insights, and the need to reduce network bandwidth costs. These forces together create a powerful opportunity for edge AI. PyTorch extends its ecosystem to edge devices via PyTorch Edge, a research to production stack for mobile and embedded deployments. SQTorch is the key runtime, an open source on-device inference engine built by Meta with partners like Arm, Apple, and Qualcomm. And SQTorch allows you to export PyTorch 2.x models into a stable, compact representation that can run efficiently across device hardware, from mobile GPUs to microcontrollers. It prioritizes portability, working across different architectures, productivity, retaining the PyTorch developer-friendly workflow, and performance, delivering low latency and a small memory footprint. SQTorch differs from PyTorch Mobile by using the new PyTorch compiler and enabling modular, customizable runtimes. It also integrates with Metal and NNAPI backends for acceleration. At the edge, we often cannot fit the entire model on one device, so we partition it across multiple devices and orchestrates the inference through a central coordinator. Each device holds a subset of the model's layers and exchange intermediate activation tensors over local networks. We use pipelines parallelization, where devices process different input tokens concurrently, and recurrent pipelines parallelism to minimize idle time. This architecture allows memory per device to shrink and throughput to increase as more devices join. We also use the data parallelism across clusters. The central coordinator handles synchronization, scheduling, and fallback to the cloud when needed. This distributed approach unlocked high-capability LLMs on low-power devices while managing latency and reliability. To make edge inference practical, we combined several optimization techniques. First, model compression uses pruning and knowledge dissolution to create smaller student models that retain performance. Second, quantization converts weights and activations from 32-bit floats to lower precision formats like int8 or FP8, reducing memory by up to 4-fold and enabling faster computation on specialized hardware. Third, distributed inference splits the model across devices, using efficient communication protocols to exchange activations. Fourth, federated learning trains and updates models on device with local data and aggregates updates centrally, preserving privacy and enabling personalization. Combining these techniques helps meet memory, latency, and accurate targets. Let's look at the performance improvement from applying these techniques. Benchmarking shows that optimization LLMs frameworks can reduce memory footprint. Oh, I think one of my figure was missing from here. Never mind. I will just verbally talk to it. So benchmarking shows that optimized LLM frameworks can reduce the memory footprint and inference latency by an order of magnitude compared to naive deployment, with minimal accuracy loss. Hardware accelerators like Amazon EC2 Inf2 provide 3 times the compute and 4 times the memory of previous generation instances, delivering up to 4 times higher throughput and 10 times lower latency. When evaluating your own deployment, benchmark memory consumption, latency, throughput, and accuracy across different quantization levels, batch sizes, and hardware configurations. Use open source tools like Torchbench and measured end-to-end latency from device into input to output. So these insights underscore the importance of careful optimization and hardware selection. Here is a case study from NDI-LLM, a model-distributed inference approach for large language models on edge devices. The model is partitioned into multiple blocks distributed across low-power devices. Each device sends intermediate activation vectors to the next device. The system uses recurrent pipelines parallelization to reduce idle time and increase throughput as more devices are added. In experiments, memory per device decreased significantly and throughput increased nearly linearly with the number of devices. This case demonstrates that with proper partitioning and scheduling, we can run large models across edge clusters while meeting real-time requirements. We'll discuss what worked well, where bottlenecks occurred, and key lessons for your own deployment. Based on our experience, here are some best practice. Choose the right model size and architecture for your use case. Smaller models or fine-tuned versions of Llama 2 may suffice. Apply compression and quantization early and profile performance to find the best precision. Int8 often offers a good balance. Use distributed inference and pipeline parallelization to scale across multiple devices. Ensure your network bandwidth and latency are sufficient. Incorporate the federated learning when you need on-device personalization and privacy. Benchmark rigorously under the real-world conditions and use hardware accelerators when available. Adopt open source stacks like PyTorch-edge and SQTorch and contribute back to the community. Keep security and privacy in mind by encrypting activation transfers and applying differentiation privacy techniques for federated learning. So here comes an open source spotlight with YOMO, connecting reason to actions. So you can see the user starting from the app and the sensors use the events IoT telemetry here. And then it connects with the YOMO coordinator, which through the quick string TLS v1.3, which is quite low latency. And then the YOMO connector here does bridges inference and execution, linking thought to action and unlocking the full value of InfiniEdge AI. You can see the YOMO coordinator here can cover geo-distributed multi-region and also cross the first auto routing to provide a high availability. So, and then it can connect if you are here calling from San Francisco to Delhi in India, and then it can reach the edge LLM there, runs the XQTorch and PyTorch edge there. And also it connects with the MCP using the MCP function calling. So it's MCP ready, and serverless architecture, strongly typed languages like the TypeScript and Golang is supported, and in the backend it supports to the SaaS. So we have been running several typical apps there. One is called we use the Whisper and to do the TTS, and we also has a fashion app called Style AI, and it can do the styling recommendation and the virtual try-on. So predictive simulation is crucial when designing AI infrastructure. Frameworks like Z-Flow-Sync model the entire AI pipeline. It's the LLM graphs, the runtime software, and the hardware characteristics, and the distributed topology, and compile them into simulation workloads. The system uses graph-based compilation and generate optimized kernels and schedule across devices, then simulate performance across multiple levels, like microarchitecture, system level, and full stack. By exploring trade-offs across hardware design, model choices, and scheduling strategies, simulation can produce actionable insight for memory provisioning, runtime tuning, and cost optimization. This helps answer questions like, shall I use a GPU or CPU? How much memory do I need per node? Which quantization level offers the best trade-off? Simulation-driven co-design aligns model engineering and hardware procurement, reducing the trial and errors in the production. To conclude, generative AI and edge computing are both growing rapidly, and combining them offers a powerful new experience, but also challenges due to the massive size and compute demands of LLMs. We discussed how PyTorch Edge and XQTorch enable on-device inference with portability and productivity and performance. Distributed architectures and optimization techniques like compression, quantization, distributed inference, and federated learning make LLMs visible at the edge, viable at the edge. So benchmarking shows that these strategies can reduce memory and latency by orders of magnitude. Looking ahead, we'll see specialized hardware, improved compilers, dynamic models splitting, and more open source collaboration. Your participation in communities like LFEdge, LFAI, and data, and InfiniEdge AI, which is part of LFEdge, will accelerate this progress. And I see I probably talked too fast. Sorry about my faster speed. I can show more details in the InfiniEdge AI to see how it goes. Give me one sec. I'm switching to the slides. Yeah. Since we're at this slide, I think it. Yeah, just we are at this slide. This is my contact. I'd love to continue the conversation, and you can scan the QR code to join our community, connect me, and access the resource. Now let me move to another site. Sorry about that. Okay. I can talk about the InfiniEdge AI updates and roadmap, because this is exactly talking how we use PyTorch here. Oh, it's not showing. I have to download it first? Okay, one sec. I'll just download and open it. Opening. Here we go. Yeah, so this is actually the slides I'm going to show at tomorrow's event. It's across the street from NVIDIA headquarters. And you can see we already deployed and released 2.1 already. Release 1.1, 2.0, 2.1. Now we're at 2.2. Here you can see the InfiniEdge AI is more like a modular and scalable, and which has the flexible components, orchestrate the AI agents across the diverse device and environment. Also, it's fast and private, and because we optimize the runtime, provides low latency inference while protecting the data from the edge. Last not least is the open collaboration. It's community-driven. Deployment invites the contributions from engineers, researchers, and enthusiasts. So this is the 1.1 highlight. What we have is the enhanced performance, which we optimize the inference engine and scheduling the reduced latency and increase the throughput on resource-constrained devices. And we unified from edge to cloud. How many minutes? I can say 5. Okay. The deep integration with Sphere and OPEA. Sphere is a runtime. OPEA is from InfiniEdge. It stands for the Open Platform Enterprise AI. It provides something more like NIM. Yeah, the open source NIM. Provides a one-click pipeline spanning edge devices and cloud services. We do have a real-time demo and no-code agents there. So the release 2.0, the serverless and data tours, I just introduced YOMO just now. It's a serverless MCP. And there's something called Edge Data Agent. It's more like a privacy-preserving analytics with LLM. Imagine you walk into the Egypt museum, right? You ask ChatGPT, and what's this and that, and where do you want to see this mummy, the new mummy? It's probably not in the internet, and no matter you through the deep research or you search on the web, it's not there yet. So there are some of the local code generation and on-premise data there. You can do the multi-step workflows for the richer insights when you are in the, this is one, okay. All right, sure. And to know more about InfiniEdge AI, I invite you to join our AI workshop tomorrow. And so far, we already have 155 people registered, and the wait list is still open. If you want to join, I can just let you guys in. I think which is the best one. Okay, I have 1 minute. So this is a key takeaway. The release 2.0 builds on 1.1 with serverless MCP, privacy-preserving analytics, unified runtime, and federated learning life cycles. So the future focus on the runtime portability, robotics, and AI ops. We have a physical AI there, and the trusted deployment. Opportunities for all of us to contribute. So I guess I have no more time, right? Yeah, it killed me. Thank you, everybody. Thank you for having me.